Usually when we think of a catastrophic machine failure, we picture something, dramatic,
No,
right?
absolutely. Like a
Yeah.
snap drive belt or just smoke pouring out of a server chassis somewhere.
Exactly. We instinctively view mechanical engineering at this really macro scale. Like you look at a robotic arm on an assembly line or a high-end aerospace actuator, and the heavy titanium just looks permanent, invulnerable.
It does. It looks like nothing could ever break it.
Right. But the truth is, the death of a machine rarely starts with a bang. It starts at a scale we can't even perceive.
A completely invisible scale, yeah.
So today, we're taking a deep dive into the microscopic world of precision transmission. We're bridging the gap between theoretical R&D and the actual factory floor.
Because for you listening, we want to show you exactly how these seemingly minor manufacturing decisions dictate whether a multi-million-dollar machine runs flawlessly for a decade or, quietly destroys itself on day one.
Yeah, and that illusion of permanence is, it's the first thing you lose when you study advanced manufacturing, isn't it?
Oh, 100%. A heavy steel gear might look solid to the naked eye, but under a microscope, it's just a landscape of potential vulnerabilities.
Okay, let's unpack this. We have to look at the extreme measures taken during the fabrication of these precision components.
Right, because we are talking about mechanisms that control satellite dishes, surgical robots, advanced optics.
Where standard machining isn't just inadequate, it's dangerously imprecise. So let's start at the very beginning of creating a precision part, right? Cutting the raw shape.
The fun part.
The manufacturing literature points us to a process that sounds, honestly, like a sci-fi concept: ultra-precision diamond turning, or UPDT.
Yeah, it's a great name.
It really is. The specs define this as utilizing single crystal diamond tools and nanoscale equipment to achieve an ultimate mirror finish, specifically for non-circular precision reference surfaces. But I have to push back here immediately. Why a diamond? Surely in modern heavy industry, advanced carbide tools are sharp enough, right? Is specifying a single crystal diamond just like an expensive way to impress aerospace clients? Or does it actually change the physics of the cut?
It entirely changes the physics of the cut. What's fascinating here is that it's all driven by the atomic structure of the tool itself.
Okay, how so?
Well, when you look at the tolerances required for precision transmission, standard carbide tools are practically blunt instruments.
Really? Blunt.
Yeah. Under high magnification, a regular cutting tool tears and smears the metal just as much as it cuts it. It leaves behind this jagged, heavily stressed surface.
Oh.
But a single crystal diamond has a continuous, uniform molecular lattice. You can sharpen it down to a literal atomic edge.
So it just slices cleaner.
Exactly. It shears the metal bonds so cleanly that you bypass that whole smearing phase entirely. You get an ultimate mirror finish directly off the lathe.
But why go to that extreme? A slightly smeared microscopic surface doesn't seem like it would cause an entire aerospace actuator to fail.
Well, it does when you introduce high-speed dynamics. Look at the specific application from the R&D data. They use UPDT for machining the non-circular cam profiles of wave generators.
Okay, wave generators.
Right. In precision robotics, wave generators often rely on an elliptical shape. It's deliberately non-circular to drive the gear reduction. The whole goal of using UPDT on that elliptical cam is to completely eliminate microvibrations.
So for you listening, imagine trying to trace a perfectly smooth oval on a microscopic level.
Yeah, not easy.
If your tool stutters or, tears the metal even a fraction of a micron, you've essentially left a microscopic speed bump on the surface of that cam.
And when you put that bumpy cam into a transmission that's running at thousands of RPMs, every single time a roller passes over that microscopic defect, it creates a micro impact.
A micro impact, which at high speeds, those must just compound, right?
Oh, rapidly. They create acoustic resonance and high-frequency vibration, and over time, that vibration travels through the assembly, loosening tolerances, fatiguing the metal.
And eventually tearing the machine apart from the inside out.
Exactly. But by using an atomically sharp diamond, the tool glides so flawlessly that those micro-vibrations are engineered out of existence before the part even leaves the cutting floor.
That is wild, but it sets up a fascinating mechanical paradox, I think. We've just sculpted this nanoscale, vibration-free shape. It's a mirror finish ellipse.
A perfect shape.
But it's still just raw, annealed metal. The second you put that raw steel under immense torque, it's just going to get chewed up.
Oh, absolutely destroyed.
So we have to harden it. But traditional heat treatment involves baking the entire part in a furnace.
Right.
And then rapidly quenching it.
Right, usually in oil or water.
Doesn't that massive thermal shock just warp the exact perfect geometry we just spent so much money cutting with a diamond?
Yes, that is the classic nightmare of precision manufacturing. You achieve dimensional perfection, and then the hardening process fundamentally distorts it. Heat causes the metal's crystal structure to shift and twist.
Right. So the R&D literature offers a really targeted solution here, laser surface hardening.
Yeah, this is brilliant.
It says the process involves utilizing a high-energy laser for rapid, localized heating, immediately followed by self-cooling quenching.
Right?
And the claim is that this creates an incredibly small heat-affected zone, resulting in almost zero deformation.
But wait, metal is an incredible thermal conductor, right?
It's generally, yes.
So if you blast a targeted layer with a high-energy laser, doesn't that thermal energy just lead straight into the core of the part and ruin the geometry anyway?
Well, that's where the timing and that concept of self-cooling quenching becomes so critical.
Okay, explain that.
In a traditional furnace, you heat the entire mass of the gear. But with a high-energy laser, you're applying intense heat to a layer that might only be fractions of a millimeter deep. And you're doing it in milliseconds. Oh, so it's incredibly fast.
Super fast. The surface flashes to a critical temperature before the underlying mass of the metal even realizes what's happening.
So the core of the metal basically stays at room temperature.
Precisely. And that cold core acts as a massive thermal heat sink.
Oh, I see.
Yeah. The second the laser pulses off, the vast bulk of cold metal underneath instantly sucks the heat right out of that hot surface layer.
So you don't even need to plunge it into a tank of oil.
Exactly. The part quenches itself from the inside out. And because the overall volume of the part never heats up, the geometry of a perfectly diamond-turned component remains completely intact.
That is so elegant. And looking at the practical applications in the notes, this localized approach is specifically aimed at the thin-walled transition zones of components called flex splines,
Right.
which a flex spline is a brilliant piece of engineering that actually has to bend and flex continuously as it rotates to drive the gear teeth.
Which is exactly why you cannot put a flex spline in a traditional furnace.
Right, because if you harden the entire component, those thin walls become brittle.
Exactly. The moment the transmission powers up and the walls try to bend, they just shatter like glass.
But conversely, if you leave the whole thing soft so it can flex, the areas taking the friction will wear down to nothing in a matter of hours.
So it's about applying armor only exactly where it's needed. You laser harden the specific transition zones, taking the friction, while leaving the rest of the thin walls soft and ductile enough to survive the constant bending.
That's amazing. It allows engineers to isolate different mechanical properties within a single continuous piece of metal.
Right, preventing local failure without sacrificing the system's flexibility.
Okay, so lasers clearly solve the problem for macro components with thin walls. But what happens when the entire component is microscopic?
Yeah, that changes things.
Let's talk about miniature gears. I mean, gears so tiny that a localized laser pulse would just melt the whole tooth, right? And a traditional abrasive grinding wheel would obliterate it entirely.
It would just be dust, yeah.
So how do you machine a surface that's too delicate to even touch with standard physics?
Well, you basically abandon traditional physics and pivot entirely to chemistry.
Okay.
When a part cannot survive mechanical force or thermal shock, we use a process called electrochemical grinding, or ECG.
Right, so the specs define ECG as a composite method combining electrolytic and mechanical grinding, where the material is primarily removed electrochemically,
Yes.
and the key result is a surface completely free of stress and burns. But I need some clarity on how this actually works on a factory floor,
Sure.
because if you're dissolving the metal with electrical current and an electrolyte fluid, aren't you essentially giving the gear an acid bath?
It sounds like it, yeah.
Doesn't that leave the surface like pitted and porous and brittle? That sounds like a terrible way to finish a gear tooth.
If we connect this to the bigger picture, it would be terrible if it were an uncontrolled acid bath. But ECG relies on highly controlled anodic dissolution.
Okay, break that down for us.
Let's compare it to traditional grinding, which is an incredibly violent process.
Right, lots of friction.
Exactly. A standard grinding wheel forces abrasive rocks against the metal, literally tearing it away. That friction generates immense heat, causes surface burns, and leaves tremendous physical stress in the molecular structure of whatever metal is left.
Like bending a paperclip back and forth.
Perfect example. The metal might look smooth on the outside, but internally, the crystalline structure is exhausted.
So if you apply that kind of violence to the flank of a miniature gear tooth, it's only a fraction of a millimeter thick.
You compromise the structural integrity of the entire tooth before it ever sees a day of work.
Wow. Okay, so how does ECG avoid that?
Well, with ECG, the grinding wheel is actually a conductive cathode, and the miniature gear is the anode.
Okay.
You flood the gap between them with an electrolyte fluid and pass a low-voltage, high-current electrical charge through the system. The metal on the surface of the gear tooth literally dissolves, ion by ion, into the fluid.
Wait, then where does the mechanical part of the grinding come in?
So as the current dissolves the metal, it instantly forms a microscopic oxide layer on the surface. That layer acts as an insulator and stops the chemical reaction.
Okay, so it protects itself.
Right. So the abrasive particles embedded in the ECG wheel aren't there to gouge the raw metal. They're just there to gently wipe away that incredibly soft oxide layer as quickly as it forms.
Oh, so it just allows the electrolyte to continue dissolving the metal underneath smoothly and evenly.
Exactly. Because the material is primarily removed electrochemically, there is virtually no friction.
And no friction means no heat, no surface burns, and zero mechanical stress left behind in the metal.
Precisely. For the delicate tooth flanks of miniature gears, ECG is really the only way to ensure they have the exact dimensional profile they need without embedding microscopic fatigue that would cause them to snap.
That is so clever. So we've chemically sculpted this tiny gear without exhausting the metal. But let's zoom in even closer on the resulting surface.
Okay, let's do it.
Because when you look at the advanced manufacturing specs, they don't just demand that a surface be smooth, they specify the surface lay.
Yes, a very important detail.
The literature defines surface lay as the specific direction of the microtexture, or the microscopic tool marks left behind by the machining process.
Right.
So what does this all mean? Why does the direction of microscopic scratches matter if the surface feels perfectly smooth to the touch?
Because in precision transmission, parts rarely ever touch each other directly. Well, at least they shouldn't.
They shouldn't.
No, they rely on elastohydrodynamic lubrication.
Okay, hold on. I'm going to need an analogy for that one.
Fair enough. Think about hydroplaning a car.
Okay.
When you drive fast over a deep puddle, the water pressure builds up under the tire faster than it can escape, right?
Yeah, and you lose control.
Right, because the tire lifts off the asphalt. The rubber is literally floating on a microscopically thin film of water.
Okay, I'm with you.
In precision engineering, we want to create that exact hydroplaning effect, but on purpose, using oil. When two gear teeth mesh under heavy torque, they should be riding on a high-pressure film of oil.
But if the pressure is that extreme, what stops the heavy metal gears from just squeezing the oil completely out of the way?
That is exactly where the surface lay comes into play. Those microscopic tool marks act as tiny channels.
Oh, like the tread on a tire.
That's a perfect analogy, yeah.
Yeah.
If the engineers specify the surface lay correctly, the direction of those grooves acts like a micropump.
So as the gear teeth slide against each other, the angled grooves physically channel the oil inward.
Yes, actively trapping it in the high-pressure contact zone and maintaining that protective film.
So what happens if a manufacturer gets lazy and the microscopic grooves just point the wrong way?
It acts like a squeegee.
Oh, no.
Yeah. Instead of trapping the oil, the surface lay actively pushes the lubricant out from between the meshing teeth.
And when that oil film collapses, what actually happens at the molecular level?
Complete devastation. I mean it. Without the oil film separating them, the two raw metal surfaces make direct contact under immense pressure and friction. The heat spikes instantly.
Oh, man.
The highest microscopic peaks of the metal on both gears literally weld themselves together for a fraction of a millisecond.
Wait, really? They weld together?
Yes, micro welds. And as the gears continue to turn, those micro welds are violently ripped apart, tearing chunks of metal out of the surfaces.
Which creates metal shrapnel inside the transmission, right? Just accelerating the destruction.
It's called spalling. Within hours or, even minutes sometimes, the gears grind themselves into dust.
That's terrifying.
It is. Specifying the correct surface lay isn't just about making the metal look neat under a microscope. It is a critical fluid dynamic strategy to keep the machine alive.
This brings us to, honestly, a terrifying climax in the R&D data.
Oh, I know where you're going with this.
Yeah. Because we've managed the geometry with diamonds, we've localized the armor with lasers, we've avoided mechanical stress with chemistry, and we've engineered the microscopic scratches to actively pump oil.
We've done everything right.
Externally, the component is an absolute masterpiece. But the literature highlights this invisible internal threat that can undo all of it. Retained austenite.
Yes. the ghost in the machine.
The data defines this as an untransformed residual structure left over after heat treatment. And over time, or under pressure, this structure slowly transforms, causing aging, deformation, in precision parts.
Right.
Here's where it gets really interesting for you listening. You're telling me we can do everything perfectly on the factory floor, put the component in a machine, and the metal will just decide to change its own shape months later.
It sounds impossible, but yes.
Yeah.
This raises an important question about longevity in engineering. When you heat steel up to extreme temperatures during the hardening process, its atomic lattice shifts into this dense, high-temperature phase called austenite. The goal of rapidly quenching the metal that we talked about earlier is to force all of that austenite to transform into a much harder, more stable room temperature structure called martensite.
But the word retained implies that the transformation doesn't always finish.
Exactly. The rapid cooling can actually trap pockets of high-temperature austenite inside the cold metal. It gets frozen in place.
Oh, wow.
But austenite is completely unstable at room temperature. It desperately wants to shift into martensite. It's essentially, holding its breath.
A structural time bomb just waiting to go off.
That's exactly what it is. And when it finally does transform, whether that's triggered by the mechanical stress of the machine operating or simply the slow passage of time just sitting on a shelf for a year, the molecular structure changes.
And what happens when it changes?
Well, martensite is physically less dense than austenite, which means when the retained austenite finally transforms, it expands.
The metal expands?
The metal literally swells from the inside out.
How do you build a transmission capable of nanoscale accuracy if the building blocks themselves are slowly growing?
You have to aggressively control the internal chemistry. The manufacturing specs dictate that engineers must minimize retained austenite to below 5%.
Okay, so there's a strict threshold.
Right. And they often do this using deep cryogenic freezing treatments right after quenching, basically to force the stubborn austenite to transform before the part ever leaves the factory.
The literature specifically notes that keeping it below that 5% threshold is the only way to ensure pitch accuracy over a long lifespan.
Yes, pitch accuracy is everything.
Because if a gear sits in a transmission for 2 years and the retained austenite causes it to swell, the pitch, which is the exact spacing and profile of the teeth, drifts.
Exactly. The teeth get thicker, the mesh binds, the friction spikes.
And the transmission tears itself apart.
All because of a microscopic chemical shift that happened years after the manufacturing was supposedly finished.
Engineers aren't just designing a machine for the day it gets turned on then. They are trying to lock the atomic lattice of the metal into a permanent state so it doesn't subtly mutate years down the line.
It's an ongoing war against the inevitable flow of time and physics.
Well, to synthesize the scale of what we've covered today, we started with cutting wave generators with atomically sharp diamonds to kill acoustic resonance.
Right.
We explored using the rapid thermal conduction of cold metal to laser-harden flex splines without shattering them.
Which is still mind-blowing.
It is. We unpacked the anodic dissolution of electrochemical grinding to sculpt delicate miniature gears without leaving physical fatigue in the structure.
Yeah.
We revealed how the microscopic grooves of the surface actively pump oil to prevent gears from micro-welding together. And finally, we looked at the cryogenic battle against retained austenite to stop metal from spontaneously expanding years after it was forged.
The sheer depth of the problem solving is staggering.
It really is.
But taking a step back, it forces us to confront this mind-expanding question.
Let's hear.
If the lifespan of today's most advanced aerospace and medical machines is entirely dictated by managing friction and metallurgy at the microscopic level,
Right.
what happens to mechanical engineering in the next 20 years?
Oh, that's a good point.
Right. When we start building complex machines and motors at the nanobot level, devices designed to swim through the human bloodstream,
Wow, yeah.
the rules we just discussed will completely break down. How do you design a gear tooth when it's only 3 atoms wide?
I can't even imagine.
Well, we have to completely invent new laws of physics and chemistry when a surface lay isn't a microscopic scratch, but a single, deliberate row of carbon atoms.
A completely new frontier where friction and chemistry become the exact same thing.
Exactly.
Well, we want to thank you for joining us on this deep dive into the microscopic world of precision transmission. The next time you rely on a high-end machine, we hope you view that solid metal not as a static object, but as a frozen battleground of nanoscale engineering fighting against the inevitable flow of physics and time.